Hey geometry class, this is going to be our lesson on 5.2, use perpendicular bisectors. And this is what we're going to be doing. We're going to be proving and applying theorems about perpendicular bisectors, mainly the applying portion of this with the exercises that we have in this section. Not very many things that we're going to be doing any proofs on. So let's move on. Okay, so in this section, like I said, we're going to be talking about perpendicular bisectors. And here's the definition of a perpendicular bisector. A segment, ray, line, or plane that is perpendicular to a segment at its midpoint is called the perpendicular bisector. And you'll see a picture of that here on this next slide of what this is exactly talking about, an image of this anyway. When a point is the same distance from two or more objects, the point is said to be equidistant. So this is just another vocabulary word that we need to know, equidistant. And again, I will show you on the next slide what exactly equidistance means using a figure. Triangle congruence theorems can be used to prove theorems about equidistance points. So whenever we're going to be getting into another chapter that we're going to be proving triangles congruent or triangles similar. Equidistant is a good definition to have, and also same goes with bisector or perpendicular bisector. So let's move on to our next slide. Okay, so here's what I was referring to whenever I told you that I was going to show you an image of something that is a perpendicular bisector. So we have segment AB right here, and this line going through AB is the perpendicular bisector of AB. And the reason I know that is because AY and YB are being shown that they are congruent. And then we have this little right angle here showing that these two segments, AB and XY, are indeed perpendicular to each other. So that's where the perpendicular part comes from. But this right here tells us that AY and YB are congruent to each other. That means that this line right here cuts AB in half. It's the bisector. So that's where we come up with perpendicular bisector, a line that cuts another segment in half and it intersects it at a right angle. Okay, so let's look at these theorems that we have here now. It says perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So it's referring to if a point is perpendicular on the if a point is on the perpendicular bisector of a segment. So it's talking about this point right here, point X, is on the perpendicular bisector. And then we should know from this given information that if XY is perpendicular to AB, we know that these two things are perpendicular. And if we know that AY and YB are congruent, then we can conclude that AX and BX are also congruent or equal to each other. Now, let's look at the converse of the perpendicular bisector theorem. It's pretty much the same thing as this up here, except like what it says, it's the converse. It's we reverse the hypothesis, the conclusion around with each other. So if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So we know that XA is equal to XB, so that these two right here are equal to each other or congruent to each other, however you want to look at it. Then we should know that this right here is the perpendicular bisector of AB. So we can conclude that XY is perpendicular to AB, and then that AY and YB are congruent. Okay, so let's look at some exercises that are going to use these things. Okay, uh, this exercise comes straight from what we just looked at with the perpendicular bisector theorem and its converse. Um, what we have here is this drawing right over here tells us that NP is the perpendicular bisector of ML, because we know this distance right here is congruent to this distance over here, and these two lines intersect at a right angle. So it says find each measure. Well, it just says find MN. Well, by the perpendicular bisector theorem, if we know that that NP is the perpendicular bisector of ML, then this right here and this right here are congruent, meaning that MN is 2.6. It's that easy. Okay, similarly, we have in this exercise, it is asking us to find each measure, find BC, what BC is equal to. Okay, so this is using the converse. We know this measure over here is 38, and then this measure over here, CA, so AC and BA are congruent to each other, and that means that DA is the perpendicular bisector of BC. So this means that DC is congruent to DB. So BC is equal to this whole area added up together. Since this segment over here is 12, then this one is going to be 12. 12 plus 12 is 24. So BC is equal to 24. And we are done. Okay, in this example here, again, we're asked to find the measure of TU, and we have to take this one a little bit further with our algebra skills. Here we are given that UW from this picture right here is the perpendicular bisector of TV, meaning that from the perpendicular bisector theorem, this segment right here and this one over here are congruent, and we can solve for x. So let's solve for x. I'm going to say 3x plus 9 is equal to 7x minus 17. Okay, and solving this equation, we can get to 26 is equal to 4x. And then divide both sides by 4, we get x is equal to 6.5. Well, we found what x is equal to, but we're asked what is the measurement of TU. And here's what the measurement of TU is. It's this right here, but we have to plug x back in here. So, plugging x back in, we can find that TU is equal to this right here. do that calculation, TU is going to be equal to, my calculator tells me it is 28.5. And there we go. We found our solution. Okay, so here's a little note about perpendicular bisectors in triangles. Since a triangle has three sides, it has three perpendicular bisectors. When you construct the perpendicular bisectors, you find that they have interesting properties. So let's look at some of those properties. Okay, so when three or more lines intersect at one point, the lines are said to be concurrent. The point of concurrency is the point where they intersect. Let's see, in the figure below, you will see that three perpendicular bisectors of a triangle are concurrent. This point of concurrency is the circumcenter of the triangle. Okay, so this figure right here, all of these segments that you see that are in red are the perpendicular bisectors of each side of the triangle. And they intersect at this point P. That is the point of concurrency because all three intersect at that one point. And this point of concurrency is called the circumcenter. Now, we have something called the circumcenter theorem. The circumcenter of a triangle is equidistant from the vertices of the triangle. So if we find the point of concurrency, which is the circumcenter here, this circumcenter, if we draw a line from that point to all of the vertices, all three of those lines that you see in blue are equal to each other. Their distances are equal, or you can say they are congruent to each other. Okay, so that is our circumcenter theorem, and that is what a circumcenter is. Here are some more things about circumcenters. The circumcenter can be inside the triangle, outside, or on the triangle. So in an acute triangle, the circumcenter is always going to be on the inside of the triangle. And then for an obtuse triangle, all of the perpendicular bisectors meet on the outside of the triangle. So that's the circumcenter. And then on for a right triangle, the circumcenter meets on the triangle. Okay? So that's going to be the three cases there. Okay, one more thing about circumcenters. The circumcenter of this triangle down here, triangle ABC, is the center of its circumscribed circle. Okay, the circle that contains all the vertices of a polygon is circumscribed about the polygon, meaning this point right here is found to be the circumcenter of this triangle. And if you use that point to draw a circle, you can use your compass. This is the center, and then stretch it out to one of the vertices of the triangle, and you are going to be able to draw a circle that circumscribes this triangle. And in a true circumscribed triangle, all the vertices will touch the triangle, just like in this picture right here. All right, so here is an example, and we're going to apply the circumcenter theorem. So here it's asking us to use this diagram that we have over here to the right, and it says find GM, knowing that segment MZ is perpendicular is a perpendicular bisector of triangle GHJ. So GM, let's look for that. GM is right here. And if we know that MZ is the perpendicular bisector, that means that GM and MJ are congruent to each other. So the answer to this, GM, is equal to 14.5. And I'm getting that number from this right here. Since these two segments are congruent, then GM is also equal to 4.5. Okay, another example, same figure off to the right here. It says use the diagram, find KG. And let's see, KG, where are you? Right here. So, and it tells us that KZ is the perpendicular bisector of triangle GHJ. So again, KG, if KZ is the perpendicular bisector, or is a perpendicular bisector, then we should know that KG, or GK, sorry, and KH are congruent to each other. So the measurement of GK is going to be the same as KH, which is 18.6. Okay. All right. Still same figure in this next exercise or example here. We're asked to find the length of JZ. Here's JZ. Okay. JZ is this line right here. So it says right here that Z is the circumcenter of triangle GHJ. So we know that this point right here is the circumcenter. If we know that point is the circumcenter, then by the circumcenter theorem, Z is, like this says right here, Z is equidistant from the vertices of triangle GHJ. Okay? And so let's see. This right here, ZG is 19.9, and that is a segment that goes from the circumcenter to the vertice. So the other segments that go from the circumcenter to the other vertices, the circumcenter theorem states that all of these segments are congruent. So by that theorem, we should know that JZ is equal to 19.9. Okay. The last thing for everybody to do is this lesson quiz. And just like the last one, we will go over this lesson quiz in class. That's how we'll begin the class, just to make sure everyone understood what was going on in this video lesson for you. So do this on your own and we'll go over it in class. And I will see you then. Goodbye, everybody.